Good afternoon. Welcome to Krishna's class. We shall continue with the proof of the theorem that the Fourier series of functions in CT, although converges in L2, no, it doesn't converge, not necessarily converge pointwise. Now, this non-convergence of pointwise is something probably of a surprise because we are working on continuous functions, periodic continuous functions defined on the interval on the real defined on. Now, this is a bit surprising because L2 convergence need not imply pointwise convergence. Now, let us prove this. And for that, we have done some preliminary work, but we will recall the crucial statements of it. Now, you have the Fourier series for f belonging to CT we take. And then we have the Fourier series. Now, CT is contained in L2 T. Therefore, the Fourier series is well defined. What you have is this, that f is plus infinity, where of course what you have is this. Now, if you want to study the convergence of this series, okay, I'll put it this way: x here for x belonging to now f is defined. F is an element of CT. Okay. That means it's a periodic function, it's a continuous function. Okay. Now we have the following. In fact, what we do is, if you have an infinite series, the way in which you look at the convergence is by evaluating it by looking at the sequence of partial sums of the series and then looking at the limit of that. So let us make some notations. The notation is this, that we can estimate the partial sum turns out to be that Sn for the function f at the point x, we'll evaluate this is equal to sigma k equal to minus n2 plus n and this can be estimated to be equal to one upon 2 pi minus pi to pi ft t n x minus t, that is a kernel dt. This we have already computed. And then we have, of course, dnt is equal to sigma minus n plus n e to the power I. This we have estimated. So these are the first two equations, and we will be recalling these equations of once a while. So our problem is this, that is, we know that converges to 0 as n tends to 2. That means you are assured of L2 convergence of the sequence. So the question that you ask is, fx converge to f of x as n tends to infinity for every x belonging to R. Because f belongs to C. This is the question that we have posed. Now, what we have is the following. We were investigating this answer to this question, and we have we make use of the Vellat-Steinhaus theorem to estimate for the estimations. Okay. Now this is the one that we are looking at. This is equation, and as here. That is, I say, limit n tending to infinity Sn f equal to f of this is the question that we are asking. But is it true? Is this, that's a big question mark, is it true? Okay. Now what we can infer from this, we have the sequence Sn converges to f in f2. And this in turn implies that there exists a sequence of partial sums of the Fourier series which converges to f f. Okay. Now that is the conclusion that we can take. pointwise. Thus, what you have is this: each f belonging to L to T is the pointwise limit of almost everywhere not everywhere, almost everywhere of some subsequence of Sn, say Snk Sn such that limit k tends to infinity of equal to f of x almost everywhere. Now this is what you can conclude as a consequence of the L2 conversion, but this is not what we are asking for. We are actually asking the question whether the sequence would converge pointwise at every point on R to the value of the function at x. Okay. Now we will try to investigate this. Okay. Now in this context, what we have is we make use of the Banach-Steinhaus theorem. So the Banach-Steinhaus theorem is suppose X is a Banach space. And Y a normally linear. This is a very general statement. We will apply this in our context and try to extract information. Okay, so this is what you have, and then what have is, so let lambda n bounded linear transformations x to y be a sequence of linear. Okay, we'll not necessarily use n but alpha. Now alpha belonging to some index set is not necessarily, it should be countable set. Then either there exists m positive which is bounded such that equal to m, and that is true for every alpha belonging to the index set, or what you have is supremum of alpha belonging to A, norm of lambda alpha is equal to infinity for all x belonging to some dense G delta in index. Now G delta is, of course, as I mentioned earlier, that it is the countable intersection of a collection of open sets. And you know that arbitrary union of open sets is open, but intersection of open sets need not be open unless it is a finite intersection. Therefore, such sets are given a new name, which is called G delta, and G delta stands for the two symbols. G stands for geoffnet and delta stands for Durchschnitt. When geoffnet in German means open, Durchschnitt means intersection. Okay, so this is how the terminology comes. Likewise, you have the terminology of F sigmas. So you have F sigmas and G deltas. You can look into the literature what they mean. You often come across that. Now we use this theorem. How do we use this theorem? Okay, so we have to rework our problem into this language. For that, we have to identify the x, we have to identify the y, and then this lambda alpha, etc. So let us do that. Now, we take x to be equal to c. It's a balance. Relative to the sup norm and this we know that this is equal to supremum of x belonging to T and with respect to that Ct is a balance space. So that is the Banach space on which we now you note that from 1 each lambda n, lambda sub n is a bounded linear functional on CT. This means that we are taking y to be equal to either r or c depending on what field we are taking. If we are working on complex valued functions, then we are taking c. Otherwise, if it is r, then we are taking. Okay. But now you easily see that this is from 1. We have seen that from the definition of lambda n, this is a bounded linear function. Now what is lambda n? So we have to make the statement of that. We use the following notations. Recall the following, that we write put over n. Now this we denote by 4, and we take x equal to 0 to begin with. And for that choice, we find equal to f0 for f belonging to CT, and for n equal to etc. Now you see that this lambda n is now this lambda n is a on the Banach space CT with norm infinity. This is what we okay. Now we estimate, and why it is a bounded linear function, we will estimate. So what is the definition of lambda n? Now from 1 each norm where dn is of course defined through the partial sums. So that is no problem. So it is well defined. Now this we designate by 6, and this is of course 5, and therefore this is 6. Right. Now we claim that goes to infinity as n times 2, from which we can apply the Banach-Steinhaus theorem and arrive at the conclusion. So this is done as follows. In fact, we give the outline of the proof. This will be proved as follows. We show that as n times to infinity. Now this of course we have this as dn norm of dn 1, where norm dn 1 is this. See? Norm of f1 is 1 by 2 pi integral minus pi to pi mod f. This is your definition of norm 1, and use that on the function dn. Further, so this we prove, and then also we show that norm lambda n is in fact equal to norm of dn. And that is the equality. See, here it is an inequality in 6, and we show that actually this is an equality. So this is the crucial part. And once we prove that and show that this goes to infinity, automatically norm lambda n goes to infinity, and we can apply the Banach-Steinhaus theorem at this stage and draw the appropriate conclusions. We will do that. Okay, let's see how this. But before that, we estimate this. Okay, how do we prove that? So, give the proof of that. See what the computations are. It needs some computation. See, the, at each stage of making some or deriving some results, you may have to do some estimations and so on, which is what you generally call a hard analysis. But the soft analysis part is the theorem, the main theorem that we use to draw our conclusion. And fitting your example or the situation to the application of the main theorem, you would have to do some estimations, and which is generally the hard part of it. That is, this is what you call the hard analysis. So let us see how this comes. Okay. Note that so this is what we call 7. That is now lambda n goes to 3. Now this we designate by 3. So we are now proving. Okay. Note that now this we have to work on this rather series or the finite series and then estimate it. So let us do that. Do it by this. Multiply on both sides of DNT by e to the power minus e to the power e by 2 and e to the power I t by 2 and e to the power minus I t by 2 and subtract. And then we have the following: e to the power I t by 2 minus n to plus n e to the power I t. And e to the power minus I by 2, I t by 2 this is equal to sigma k equal to minus n to plus n e to the power I k minus half now subtracting one from the other. We have IT by 2 minus n to n sorry. Therefore, we have this is actually 2I sin t by 2 we will just write the terms from minus n all the way to n, but we shall make the observations. Some cancellations take place. With minus n we are writing. The n term is the following. These are finite sums. Therefore, all these operations do make sense. Okay. Now you see that between this term and the previous term, there are some kind of cancellations taking place. Between this term and the next term, some cancellations take place. So that keeps on happening, and eventually, after cancellations, after cancellations, you obtain two I sin t by 2 equal to e to the power I this comes from the last term and this comes from the first term, that is minus and this turns out to be, for all just routine computations. You could possibly ignore that, but I just want to show you how this comes. If I just simply write, it may look as though it is came from nowhere. So this is equal to 2I Sin n plus half consequently n plus half that's a beautiful expression. It's very compact and we designate this by and this is the one that we use for further estimations. Now we use the following. So here we use a well-known inequality. We have the following. We can use this from 9 we have the following is given. Two by pi 0 to pi dt upon. Now this we shall estimate. This is done as follows. Now dn1 t by 2 and that we write as, see, from minus pi to pi we go to this 0 to pi and we also use this inequality on this term that mod sin x is less than or equal to x on this one. Therefore you get this is equal to 1 by 2 pi dt. Now this is the integral that you come. Now what we have is this integral minus pi to 0 mod sin n plus Suppose we change the variable and we want to go to 0 to pi. Because this term we retain as it is, the first term, and the second term we try to estimate, and thus by change it is t equal to minus s, t equal to minus s. So if you do that, this is what you obtain. So if you put t equal to 2s, so we see that this is equal to t by 2. This is equal to 0 to pi divided by this by 2 ts, and this is equal to, this turns out to be integral 0 to pi ds. Therefore, now we substitute for that, and consequently now we equal to 2 by 2 pi integral 0 to pi dt, which is estimated as greater than 1 by pi. So this term we estimate sin x mod sin x is less than mod x. We make use of that, and if we make use of that, this is equal to 1 by pi 0 to pi. That there is a cancellation taking place here. 1 by pi 0 to pi now this in fact you can write as 2 by pi in an obvious way, 0 to n plus pi Because you get from 0 to n plus half pi, you will have to split and add, and you see you get a term from here, and that actually cancels out. Okay, so this is greater than 2 by pi. So this you have to split from 0 to pi by 2, etc., etc. I mean, for all values of n, you will have to work with that. Okay. So first take n equal to 0. So 0 to pi by 2, then pi by 2 to 3 pi by 2, etc., etc. So in that way, you will have to estimate, and this will give you sigma dt, and this you can easily integrate and sum up, and this is what you end up with. This is equal to 4 by pi square sigma 1 by k. So that is the estimate. dn1 is greater than or equal to plus dn1 and this, you know that this goes to infinity as n tends to. So we have got the estimate. So what we conclude is that so this is the conclusion that we get from them. Okay. Now you see that. Now fix and put gt equal to 1 if and gt equal to minus 1 if less than. This is the crucial. Okay, so for each n you do this. Then what happens is there exists functions fj belonging to ct less than or equal to 1, and so what we are approximating is each step function, that is, which has the value minus 1 and plus 1. This is approximated by the functions in CT which are continuous functions. We make use of that and use this possibility of fjt going to gt. Possibility, the actual reality. So we have now a sequence Fj. Okay. So gt is a step function. It takes either the value +1 or -1. And fj is a sequence of functions in ct which converges to gt. Okay. Such functions do exist. Now we apply the convergence theorem. We can interchange the limit and the integral. This is what you get. Limit j tending to infinity so that on the interval -pi to 0 you get fjt positive value. Okay, and on the other side you will get negative value. So we will prove this. So write equal to fj0 from our definition. And this is equal to 1 by 2 pi integral -pi to pi fjt dt etc. And this is equal to 1 upon 2 pi dt. Now this I can write as to change t to -t and then work it out, and that's easy to see. And this is equal to 1 by 2 pi integral -pi to pi g of -t and that's equal to and this essentially we have already seen that this goes to infinity. Okay. That's what we have. And so that is the proof of that. Okay. Consequently, now we can apply Banach-Steinhaus theorem. And conclude that Sn star, which we have defined earlier, which is equal to supremum of this is equal to E. And this is true for every f in some tens G delta set. This is the conclusion that we draw. So we apply the Banach-Steinhaus theorem. Now you see, a general comment about this is that often in mathematics we will have to, when we prove a particular result, you can use what is called the soft analysis as well as the hard analysis, combining the two, the power of the two together. Often soft analysis will carry you to a long distance, and once you reach there, eventually you would have to do some estimations, which are often hard estimations depending on the particular functions that you choose, their properties, etc., etc. So that's why this terminology is there. It's something called, that the general theorems that you prove in our functional analysis are generally the tools for the soft analysis. And once you reach at some stage using that, you would have to use the so-called hard analysis. That means draw conclusions from it, which would need really some finer estimates. Okay. Now we make some remarks. Choice of equal to 0 is for convenience. For any fixed x, this similar analysis would work. That is the meaning. Therefore, what do we conclude? We have the following conclusion. To each x belonging to R, there corresponds a set that means a collection of functions which you denote by x to designate the fixed x that you choose, which is a dense. Effectively, you are making use of the second part of the Banach-Steinhaus theorem. G delta in CT such that infinity. The conclusion is that you don't have pointwise convergence. That is, Fourier series of each x diverges at x, and hence this is the conclusion. What does this mean? This leads to our conclusion that the Fourier series does not converge for at every, but to the pointwise at each x. I mean, when I see this ex is a g delta. Okay, so pointwise negative this is a bit of a this indicates some of the complexities that you encounter. Outwardly, the moment you take continuous functions, you get a feeling that you will get pointwise convergence of the Fourier series, but that is not so. Okay, right? And this is what we have concluded. Now we will make some further remarks later, and we conclude today's lecture at this stage. Thank you very much.